Hello everyone, my name is Ruku Raju. So today in KP classes we'll be discussing about geochemistry. So we all know geochemistry is a very important topic for all the competitive exams related to geology. It deals about the geochemical classification of element, radioactive dating, some classification of meteorites, thermodynamics portion comes under geochemistry. So when it comes to the syllabus that we cover, these are the major topics that we have to cover for all the competitive exam. For IIT JAM, we don't need to study the whole portion. We just need the radioactive dating and the stable isotope dating and geochemical classification, some portions only. Whereas for GATE, NET and the UPSC Geoscientist prelims paper, we have to study in detail about cosmic abundance of elements, distribution of major, minor and trace elements in crust and mantle, uh, isotopic evolution of crust and mantle reservoirs, radioactive decay schemes and their application to geochronology and petrogenesis, stable isotopes and their application to Earth system process, redox reactions and EHPH diagrams and their applications, elements of high temperature and low temperature geochemistry, thermodynamics. So when you come to these portions, actually these are very important. In GATE, mainly minimum 3 questions come from this section. Sometimes 2 to 3 questions will be there minimum in GATE paper. In NET also there will be 3 to 4 questions will be there from geochemistry portion. In GSI maximum 2 questions can be asked from the from the geochemistry portion. Numerical questions do come from this section. This is a very important part. Geochemistry is a very important part when it comes to the numerical questions. They ask numerical questions related to radioactive decay schemes, the equations related to that, half-life, mean life, or the number of parent atom, number of daughter atom. Those equations are very important. When it related to stable isotope also questions can be asked. Del oxygen value questions can be asked. EHPH equation is very important. They have asked multiple times in GATE also, in NET also these questions. Elements of high temperature and low temperature geochemical thermodynamics part is also very important for numerical questions. And in GSI mainly they ask about the mantle reservoirs, the different types of mantle reservoirs, and the trace elements and their applications. Those are the things that the evolution of earth, geochemical evolution of earth, isotopic evolution of crust and the mantle, these are very important for GSI in the with respect to GSI paper. These portions are very important. So in NET, even this cosmic abundance of element is also important. You should know how the elements are, the abundance of elements present on the earth as in a universe, how the abundance of elements are. So the whole topic is actually very important for all the competitive exams. So geochemistry is a very important topic. So today let's start with the portion that is of trace elements. So as we know, a rock is a mixture of minerals, or it consists of a lot of elements present in a rock. So depending upon the weight percentage of elements present in the rock, we can divide the elements into major elements, minor elements and trace elements. So major element means weight greater than 1 weight percentage of the rock is of that element. Minor means 0.1 to 1 weight percentage. Trace element means less than 0.1 weight percentage. The elements that has less than 1% weight percentage of in the rock, less than 1.1 weight percentage is of a particular set of elements, those are called as trace elements. So even though the amount present in a rock is much lesser, trace elements are only less than 0.1 weight percentage in a rock, but still their application is much higher. We can use the trace elements present in a rock to find the magmatic evolution, to define the age of the rock, to define the like the processes that has happened from the time of crystallization till now, etc. There are so many applications for the trace elements. This only 0.1 weight percentage of elements present in a rock. So this trace element concentration varies from rock to rock. Simply trace elements during crystallization of magma, they get substituted for a major element in the structure, in the in the crystal structure, or they may remain in the melt, or they may remain in the magma. For example, potassium, it is a trace element in mid-oceanic ridge basalt. It is a trace element in mid-oceanic ridge basalt, whereas we all know potassium is one of the major element in granite. Granite, it is not at all a trace element in granite. So in different rock, for a different element will behave separately. So a particular element may be a trace element in a different rock, and it can be one of the major constituent of an another rock. Okay, so a trace element concentration varies from rock to rock. During crystallization of a particular mineral, the trace elements will be substituting for a major element in the crystal structure, or sometimes they may not even participate in the crystallization. They will remain back in the magma depending upon their property. Like this has the that depending upon the affinity of trace element to that particular crystallizing mineral. So we can divide the trace element into two: compactable trace elements and incompactable elements. The entire elements can be divided into compactable elements and incompactable elements. Compactable elements means that are concentrated in solid relative to liquid. Concentrated in a solid relative to liquid are called as compactable elements, whereas incompactable element means the one that are concentrated in liquid relative to solid. Those are called as incompactable elements. So compactable elements, they fit easily into the crystal structure. Fit easily into crystal structure. Crystal structure, that's why they are more in the solid relative to liquid. They can fit easily into the crystal structure of a mineral. Okay, now when it comes to the incompactable elements, they do not easily fit into the crystal structure of a mineral. Do not fit easily into crystal structure of a mineral. Now, the incompactable elements and compactable elements. Incompactable elements are most have large ionic radius. Whereas the compacted elements are mostly smaller, have small ionic radius. Now, some of the most important or most common compactable elements are nickel, chromium, cobalt, vanadium, etc. These are the major these are the more common compactable elements, whereas the common incompactable elements are rubidium, neodymium, yttrium, uranium, thorium, zircon, etc. All these are considered as the incompactable element. Hafnium, here scandium is also a compactable element. We can include hafnium also. Excuse me. Yeah. So this is the compactable elements and incompactable elements. So trace elements can be divided into two on the basis of their affinity towards liquid or solid. When a magma crystallizes, whether the trace element will prefer to go into the solid, or whether the trace element will prefer to stay in the melt. Depending upon that, we can divide the trace element into two: compactable and incompactable trace elements. Compactable trace elements have concentration in solid relative to liquid. Incompactable trace elements have concentration in liquid relative to solid. The compactable ones fit easily into the crystal structure. Incompactable elements do not fit easily into the crystal structure. crystal structure of minerals. Now, compactable ones are comparatively smaller ionic radius, whereas most of the incompactable elements have larger ionic radius, and have provided some of the important compactable and incompactable elements. Now, when it comes to each element, each trace element, there is its efficiency to an element, efficiency to an element to in partitions into efficiency of an element to get partitioned into a particular phase, whether it will go to the magma stage, the liquid stage, or whether it will go to the solid stage. Its efficiency to get partitioned into a particular phase is controlled by charge and ionic radius. Charge and ionic radius. So these are the two conditions, like charge valency of the element or the ionic radius of the element. These two terminologies defines the efficiency of an element, efficiency to which an element partitions into a particular phase, and that is controlled by charge and ionic radius of the element. So how can we predict? So if I have two elements are there, two different types of elements are there. So how can I say like which one will stay in the magma, which one will go to the mineral structure? So how can we predict? So this how the trace elements behavior or trace elements affinities to liquid state or to solid state is defined by Goldschmidt's three rules. So this is based on, as I said, radius and charge. These are the two factors that defines the efficiency of an element to partition into a crystal structure or to stay back in the magma. So this is defined by the radius and charge of the element. Now, Goldschmidt has defined three rules. Depending upon the radius and charge, what will happen to the trace element, whether it will stay in the melt or whether it will go into the in the crystallizing phase, whether it will get into the mineral structure. So first one is, if two elements have same ionic radius and same valency, same charge, so what will happen to two elements that have same ionic radius and same charge? They behave the same. That's what the first rule of Goldschmidt says, that two ions with same ionic radius and charge behave the same. They behave the same. So what will happen when they behave the same? They will be entering like in the same proportion, they will enter into a mineral structure. Like if both of them have the same behavior, then both elements will get into 50-50% or 25-25%, whatever, in equal way or in the same way they behave, or they will get into the crystal structure. So this particular behavior or this particular substitution is called as camouflage substitution. Camouflage substitution. Major example is rubidium in potassium feldspar. Rubidium in potassium feldspar. So what happens is, rubidium and potassium both have similar ionic radius and similar charge. So both behave the same. So hence, rubidium can substitute potassium in the potassium feldspars. So camouflage substitution happens to rubidium in the potassium feldspars. Okay. Now next, let's see. So second case where the ionic radius is different. Different ionic radius, same charge. two elements that has different ionic radius and same charge condition. So what will happen to this case? The larger one will prefer, the larger the ionic radius, which element has a larger ionic radius, they will prefer to stay in the melt. Larger ionic radius element will prefer to stay in the melt, whereas the smaller ionic radius element will prefer to go into the mineral structure. Mineral structure means solid. Simple. Larger one, it is easier to crystallize the smaller one. It is easier for a smaller element to fit into a crystal structure. So even though if both elements have same ionic charge, one will be getting into, or one can incorporate the other one. For example, strontium and rubidium. Strontium, rubidium both have same, rubidium and strontium both have same charge, but rubidium has higher ionic radius. It is much more larger ionic radius than the strontium. So what happens when crystallization occurs? Rubidium will prefer to stay in the melt comparing with strontium. Strontium will prefer to get into the, when you compare with rubidium and strontium both of them has same charge. Strontium has lesser size, or the ionic radius is smaller. So strontium will be crystallizing more, will get into minerals more than that of rubidium. So we can say that the rubidium is more incompatible than strontium. Rubidium is more incompatible than strontium. Okay. Now the next case is the third rule defining. So what is left? First we say both radius and charge are equal. Then if ionic radius is different, charge is same. Now obviously charge is different. Two elements that has different charge but same ionic radius or same size. So what will happen in this case? Here higher the charge element, the element that have higher charge will get into the solid over liquid. Higher charge one will get into the solid, lower charge will get into the liquid. Okay, so these are the three rules defining the trace elements affinities towards a liquid state and the solid state, whether they behave compatible or whether they behave incompatible. That is defined by the three rules, and it is actually defined the efficiency of a trace element to get partitioned into a particular phase is controlled by radius and charge. Hence, if both of them have same radius, one will substitute the other, that is the camouflage substitution. Both of them will behave the same. If ionic radius is different and the charge are same, then the larger ionic radius element will stay in the melt, smaller one will stay in the liquid state. Sorry, smaller one will stay in the mineral, can get into the mineral structure, or the smaller one can participate in the crystallization of a mineral. Third one, if the charge is different and it has the same ionic radius, higher the charge will stay in the solid, lower the charge will stay with the magma. Okay, so now to quantify this amount, like how partitioning happening a trace element, what is the value of its incompatibility or what is the value of its compatibility. So to quantify that, we have come up with a terminology called as partition coefficient, or it is also called as distribution constant. Partition coefficient or distribution constant. Simple. The chemical fractionation of a trace element, of an element, is unevenly under equilibrium condition, and that is defined by partition coefficient. Chemical fractionation of an element, unevenly under equilibrium condition is defined by partition coefficient or distribution constant, which is notated by the letter KD. In different textbooks, they uses different way to represent the terminology partition coefficient or distribution constant. Here I use the term KD terminology. Now KD is equal to CS divided by CL, whereas CS is the concentration of a particular element in solid divided by concentration of that same element in liquid. This is what is called as partition coefficient. So it is a ratio of concentration of an element in solid phase to that of that same element in concentration of that same element in the liquid phase. This is called as partition coefficient or distribution coefficient, distribution constant. Simply, when a mineral crystallizes, if I have a magma, if there is a magma present, liquid magma, and from this magma a particular crystal started crystallizing. Now when this crystallization of this mineral happened, if for example there is an element called as X, so I should know whether this element is compactable in this mineral or whether it is incompactable in this mineral. So what I will do after crystallization of this mineral, I'll check the concentration of X in the melt, the residue, the melt present, and concentration of X in the mineral. So for trace elements analysis is mainly done by spectroscopy. So there are XRD, XRF, there are so many spectroscopies which we can do on our rock samples that will give the concentration of major elements, minor elements, trace elements, everything. So we can analyze the concentration of trace element in the liquid and the solid, and if you take the ratio of concentration of this element in the solid to that of liquid, excuse me guys. So if this ratio comes less than 1, if this KD value comes less than 1, then we call the element X as incompactable element. Why? Because why is it incompatible? Because if the ratio comes less than 1, that means denominator is larger than the numerator, or denominator here is concentration of element in the liquid. So if this element is more in the liquid than the mineral phase or than in the solid phase, that means it is more, it want to stay in the liquid phase much higher, or it is more stable in the liquid phase than in the, its affinities towards the liquid phase is much higher than that of its affinities with the solid phase. That means it is an incompatible element, or it is an incompatible trace element. So if KD value comes less than 1, that element is an incompatible element. If KD value is greater than 1, then then the element is actually a compactable element. Compactable element. Greater than 1 means concentration of element in solid is greater than that of concentration of the same element in the liquid. That means this element can fit into a crystal structure, and that is affinity towards the solid phase is higher than that of the liquid phase affinity. Hence, it is a compactable element. So, KD value less than 1 means an incompactable element. If KD value of an element comes as greater than 1, that means it is a compactable element. And if KD value of an element comes 1 in a particular mineral, like in a particular mineral, KD value is coming 1. That means KD value of an element comes 1. That means it is neither compactable nor incompactable. It behaves the same with liquid and the solid phase. Whatever percentage concentration it went into the solid, it equal percentage it left back in the melt during crystallization, or during melting. When the mineral was melting, same amount of concentration of the element went to the melt phase, and same concentration stayed in the solid phase. That means it is neither compactable nor incompactable. nor incompatible. Now, if Kd value comes as 0, that means it is a perfectly incompatible element. The entire numerator part goes 0. That's why the value becomes 0. That means it is perfectly incompatible. Perfectly incompatible. So what we have discussed over here, simple, an element, whether the element has an affinity towards a mineral, whether the element is partitioned into the mineral phase while crystallization, or whether the element stays in the mineral while melting. So whether it has the affinity to stay in the solid phase or whether it has the affinity to stay in the liquid phase. That is quantified by the terminology partition coefficient or distribution constant. For example, if a mineral olivine is crystallizing and we are talking about the element nickel. So in the liquid, and imagine olivine crystal is being melting. So a melt has been formed. This is the melt. Now the concentration of nickel in the liquid, concentration of nickel in solid. I calculate the concentration of nickel in the olivine mineral, and when the melt from this particular mineral, like when it got molten, the amount of nickel present in the melt. So if I calculate the Kd value of nickel, concentration in solid, nickel concentration in solid divided by nickel concentration in liquid, and if this value is greater than 1, that means nickel is compactable in olivine. Nickel is compactable in olivine. If Kd value comes greater than 1, that means nickel is compactable in olivine. Actually, nickel is a compactable element in nickel is a compactable element in olivine. So olivine is a mineral, and in that mineral, nickel as an element, whether it is compactable or incompactable, defined by the terminology partition coefficient. So depending upon whatever value I get over here, that defines how compactable is an element or how incompactable is an element. That is defined by the partition coefficient terminology. Now, as we know that a rock is not only simply consisting of a single mineral. For example, a single set of rock may have 3 different types of minerals. So this is a single rock, for a garnet lahersolite or a peridotite, simple any a garnet, a granite or a medoshanic rich basalt, a single rock over here. Rocks are aggregate of minerals. There are different minerals present. So this is A mineral, B mineral and C mineral. Now, if I want to analyze whether an element, for example nickel, whether nickel element is compactable in this whole rock or whether the nickel element is incompactable, or whether the amount of nickel is higher in the rock or lesser, or whether it is compactable to the whole rock or not. That is defined by bulk distribution constant or bulk distribution coefficient defines bulk distribution constant or by coefficient defines the percentage or the compactability of an element in a whole rock. That is defined by bulk distribution coefficient. So there a single rock consists of different minerals. So and whether the nickel is compactable in this rock or not, that is defined by bulk distribution coefficient. Bulk distribution coefficient is notated by the letter D, is what we use to define the bulk distribution coefficient. So it depends upon the weight fraction of each of these mineral. Weight fraction of minerals contributing to the melt. That is what is defined by the that is what one of the factor of bulk distribution coefficient. That means what is the weight percentage of mineral A, what is the weight percentage of mineral B, and what is the weight percentage of mineral C in the whole rock. Maybe A is weight percentage of A may be 60%, B may be 20%, and C is also 20%. So this is the weight percentage. You have to consider the mass or weight percentage. We are not considering the volume percentage over here. We are considering the weight percentage of the mineral present in the rock. Okay, so weight percentage of each mineral present in the rock is one of the factor that defines the bulk distribution coefficient. So how to calculate the bulk distribution coefficient? We know from the previous partition coefficient equation, we know we can calculate the Kd value of nickel in mineral A, and Kd value of nickel in mineral B, and Kd value of nickel in mineral C can be calculated, right? Kd value of nickel in mineral A means the whether the amount of nickel present in the mineral A, and the Kd value of nickel in B means amount of nickel that is present in B, and that of C means amount of nickel present in C, or the ratio of concentration of nickel in mineral to that of the liquid, ratio of concentration of nickel in mineral B to that of the liquid, ratio of concentration of nickel in mineral C to that of the liquid is defined by the Kd values. Now, and we know the weight percentage also known. Weight percentage of A is also known. Weight percentage of B is also known. Weight percentage of C is also known. Now, by using all these terms, we can calculate the bulk distribution coefficient. Bulk distribution coefficient is Kd value of nickel in A into weight percentage of A plus Kd value of nickel in B into weight percentage of mineral B plus Kd value of nickel in mineral C into weight percentage of mineral C. So summation of, simply if I write it, D means summation of Kd value of the element X in all the minerals A, whatever it is, into the weight percentage of that mineral. So summation of this, how many minerals, there may be 6 minerals present. So the whole 6 minerals Kd values of that particular element and its weight percentage, multiply the Kd value and weight percentage of the Kd value of a particular element in that mineral and the weight percentage of that mineral, multiply it together, add of same values of different minerals, add it together, you will get the bulk distribution coefficient, which defines the amount of or the distribution of an element in a particular rock. That is what is defined by the bulk distribution coefficient. Now here the usually numerical questions do come from this section. This is one of the numerical question. A rock consists of 60% of olivine, 25% of orthopyroxene, 10% of clinopyroxene, 5% of garnet. Bulk distribution coefficient of strontium in the rock is dash, provided the partition coefficient of strontium in olivine, orthopyroxene, clinopyroxene and garnet. Partition coefficients are provided. So we know bulk distribution coefficient equation is D is equal to summation of weight percentage into the Kd value of strontium, Kd value of strontium in each of the mineral. That is what is D. So we know if I calculate D is equal to, first let's take olivine. Olivine's weight percentage is 60%. That means 0.6 into 0.014 plus 0.25 into that of orthopyroxene. Kd value of strontium in orthopyroxene is 0.040 plus 0. The percentage of clinopyroxene is 10. So 0.10 into What is the KD value of clinopyroxene? Is 0.060 plus garnet weight percentage is 5%. That means 0.05 into 0.012. That is the KD value of garnet. KD value of strontium in garnet. So if you solve this out, you will get the bulk distribution coefficient of strontium in the rock. The rock that consists of olivine, clinopyroxene, orthopyroxene and a garnet. In these bulk weight percentage, 60% of olivine, 25% of orthopyroxene, 10% of clinopyroxene and 5% of garnet. The partition coefficient of strontium in olivine is 0.014, that of orthopyroxene is 0.040, clinopyroxene is 0.060, garnet is 0.012. So equation for calculating the bulk distribution coefficient is summation of weight percentage of each mineral multiplied by KD value of strontium in each mineral. So I don't know why I put a, sorry, there is no percentage sign. So D is equal to 0.6 means because 60% of olivine. So though it is in percentage value, here you have to remove the percentage. That's why it becomes 0.6 into KD value is 0.014. 25% 0.25 into 0.040. 10% becomes 0.10 into 0.060 plus 0.05. 5% is 0.05 into 0.012 is the KD value of strontium in garnet. So if you solve it out, you will get value of 0.25, 0.025 something value you will be getting. You guys check the value, and if you guys have any doubt related to this section, like if you are not getting the equation or if you are not getting the value, let me know in the comment section. We'll help you out over there. Okay, so today simply we have defined about the bulk distribution coefficient, partition coefficient of terminologies related to the trace elements in the geochemistry portion. So geochemistry is a very important topic in GATE, NET, GSI and IIT JAM papers. In IIT JAM minimum 2 questions come. In GATE, in all the papers minimum 2 to 3 questions do come from this single subject. So it is a very important topic. Conceptual questions come and numerical questions come. In GATE mainly numerical questions come from geochemistry, thermodynamics portion and other parts of geochemistry. From NET also it is numerical questions will be asked. In GSI mainly conceptual questions will be asked from the geochemistry portion. So I hope it's the trace element portion and what is compactable, incompactable elements, what is a partition coefficient, what is bulk distribution coefficient, terminologies are clear for you. Thank you so much.